Hey guys, this is Taylor Perry, your chemistry teacher. This video is intended for my honors students. I noticed you guys were having some trouble with the honors electrons worksheet. I took a look at the lesson and I thought that, I don't know if they explained a lot of the information super well. Specifically this part. I think a lot of people are having trouble with orbital notation. So we're going to look at all these parts and I'm going to show you how I sort of thought my way through this. Let's start by just looking at your lessons because you found all this information in two different lessons, okay? The first lesson was just the quantum models, okay? That was the standard, the standard lesson that both standard and honor students had to watch. And then you also had the honors electrons, okay? That was obviously the honors portion. So I'm going to talk about both of those things because in both lessons, they talk about these four quantum numbers, okay? The first one is the principal quantum number, which I think they talk about here. Remember that every atom has, electrons orbit the atom, but they don't just orbit in a random fashion. They have these different levels, okay, these different energy levels that you can find an electron at. So for instance, if I told you that a specific energy level had the quantum number n equals 3, okay, n equals 3, what I'd be saying is that this electron is somewhere in this floor. If you want to think of it like a building, right? Like this is floor 3. So if an electron had the number n equals 3, it'd be here. If it had n equals 5, guess what? It'd be here, okay? So they talk about all the different numbers. They talk about subshells. Basically, there are four types of subshells, S, P, D, and F. And what that means is just like let's take a stadium, right? Like a stadium has different floors, and in each floor there are also different sections. You can think of those subshells as sections. So for instance, if I said that an electron had the electron configuration of 3D, okay, 3D. What that's saying is it's in the third level, okay, row 3, and it's in section D. So wherever section D is, it's in that section. If it had 3S, it's in, the third floor, but section S. If it had 2S, it'd be in the second floor, section S. All right, and it doesn't really show you these sections because, well, unfortunately, the quantum world isn't so nice and ordered like an actual stadium is. But that's what those different things mean, okay? Now, what I want to show you is I think it was on page 6 here. It talks about writing out electron configurations, which is sort of like, it's kind of half of what this is. This orbital notation, the first step is understanding the electron configuration. And let me explain what that means, okay? So, this thing called the Aufbau principle basically says that the order in which atomic orbitals are filled is based off potential energy of each position. And then it shows you what that order is. As you go through here, it shows you the order. And if you write that out, it looks really weird. You notice there's sort of a pattern here, but I went ahead and I typed it out on these notes here. And if you look here, here's the order at which electrons fill up orbitals. It starts 1s, then goes to 2s, then 2p, then 3s, then 3p, then 4s, and 3d. It doesn't feel very structured. It doesn't feel very ordered and organized. Like I wouldn't have been able to guess this. I wouldn't have been able to see any pattern here. But you don't have to memorize this. You can just use this in your notes. Like you do not have to memorize this pattern. But it will help you with your assignment. Okay, now we're gonna look back at this in just a second. I promise this will all come together nice and easy at the end. Just bear with me. I'm gonna go to the honors section here because they talked about all four of these numbers as well in the honors section, but they went into more depth. And I really like this table right here. It talks about the magnetic quantum number. It says it represents the specific orbital an electron is likely to occupy. What that means is that, it says it right here, each sublevel or subshell, so what they're talking about is those S, P, D, and F subshells. It says they each have a specific number of orbitals. So think about it like this, right? Just like a stadium has floors and sections, it also has rows. So you could think of these as rows, okay? And how many rows are in each section? Well, according to this, section P has -1, 0, and +1. What that means is it has 3 orbitals, right? 1, 2, 3. So you see how there's 3 numbers here? -1 is one number, 0 is a second number, and +1 is a third number. So there's 3 orbitals. D has 5 orbitals. F has 7 orbitals. S only has 1 orbital. I know that sounds confusing, but don't worry about the confusing aspect because, again, you don't have to know exactly why this is the case. You just have to know. And you don't really have to know, you can just write this in your notes, and I have it right here, that the S subshell has 1 orbital, the P subshell has 2 orbitals, the d subshell has 5 orbitals, and the p subshell, I'm sorry, not 2, 3, my bad. The p orbital has 3, the p subshell has 3 orbitals, my bad. It says right there, I don't know why I wrote that. So anyway, and then I also put here that only 2 electrons can fit in an orbital. So what that means, and it shows you, where does it show you here? Somewhere in here. It says each orbital can only hold 2 electrons, okay? So think about that. Think about that. Each orbital can only hold 2 electrons. So think about this. If you were to think about this, if S only has 1 orbital and 2 electrons can fit in that orbital, that means that S can have a total of 2 electrons. Now P has 3 orbitals, right? And since each orbital can hold up to 2 electrons, what's 3 times 2? Well, it's 6. So that means in total, P can have 6 electrons. Okay, and so on and so forth. So like 7, right? F has 7. Well, what's 7 times 2? That's 14. So F can have 14 electrons. Okay, and then lastly, Hund's rule says, and it sounds kind of spooky, but that orbitals of equal energy are each occupied by 1 electron, each spinning in the same direction before any orbital will receive a second electron. Now, I'm going to show you what all this means in just a second. Oops. All right, sorry about that. Okay, so why don't we look at these practice problems here? It says draw the orbital notation for an atom with 15 electrons, 25 electrons, and let's call it 24 electrons, and 9 electrons, okay? So orbital notation, it's basically a way of taking all 4 of those quantum numbers and putting them into a visual here, okay? So let's start here. Let's start with the one that says 15 electrons, all right? Now, we know that electrons, according to the Aufbau principle, electrons fill orbitals in a specific order. And that order starts with 1s. So let's start there. What we're going to do is we're just going to write down, I'm just going to write down right here, 1s, okay? 1s. Now, let's think about this now, because 1s is going to have a certain number of orbitals. And if, according to this, it says 1s, or I'm sorry, just s. S has 1 orbital, okay? So what I'm going to do is for that 1 orbital, I'm going to draw a box, okay? Not a very good, oh, that is a good box. I guess I have, okay, yeah. I have this box, and that represents the 1 orbital in my 1s level, okay? Now, how many electrons can fit in this one box? Well, each box or orbital, okay, can only hold 2 electrons. So what we're going to do is we're going to fill in these 2 electrons here, okay, these 2 electrons. And here's how it looks, okay? Because we're going to draw these arrows, all right? An up arrow and a down arrow. And the reason we're going to do that is because it says that orbitals of equal energy are occupied by 1 electron, each spinning in the same direction before any orbital will receive a second electron. So we drew the first one, and that was spinning upwards. Well, there's no other orbitals, because S only has 1 orbital. So then we just draw our second electron. Okay, so it goes up arrow, then down arrow. Let's keep going, because we don't have anything else we can do with 1s. Let's go now on to 2s. And it's going to look pretty similar. 2s. And again, same thing. I'm going to draw a box. It doesn't look, well, these aren't going to be even, because I'm not a great artiste. But let's keep going. So 2s. It has 1 box, because again, S can only have 1 orbital, right? So we're going to keep going. We're going to draw an arrow going in this direction. And there's no other orbitals because S can only hold 1. And so now we're going to draw our next arrow going down. Okay? Great. Let's keep going. Let's go on to the next thing here. And it says the next in the order, the next thing is 2p. So let's draw 2p right here. Now, what's different here? Instead of S, we have p, right? Well, look at p. It says P has how many orbitals? How many orbitals can P have? And it says it can have 3. So guess what? We're not drawing 1 box this time. We're gonna draw 3 boxes. Okay, we're gonna draw 3 boxes. So let's do that. Let's draw 1. And let's make that a bit bigger. 1, 2, Oh, that's a horrible box. 3. Okay, so 3 boxes, because again, it says that P has 3 orbitals. So these boxes represent those orbitals. And it says only 2 electrons can fit in each orbital, so we're only going to have up to 2. Now, I want you to see the order in which I do this, okay? I draw one up arrow, another up arrow, another up arrow. Now, why didn't I go up arrow then down arrow? Well, because look at Hund's rule. It says that orbitals of equal energy are each occupied by 1 electron. Okay, so what that means is all these orbitals have the same energy, right? Because they're the 2p. These 3 orbitals are all 2p orbitals. So since they're the same orbital type, right? They're all 2p orbitals. We have to have them spinning in the same direction before we get a second electron. Okay, so before each of these boxes get a second electron, all 3 of them have to be filled with 1. So it has to go 1, 2, 3 before you can go like 1, 2, 3, 4, 5, 6. But now that all 3 of them are filled, we can now fill in the down electrons, okay? So let's do that. Let's do that here. So we'll go down, down, down. Okay? Now, first off, let's count how many electrons we have here, okay? So remember, these arrows represent our electrons. So we have 2, 4, 6, 8, 10. So how many electrons do we have left? Well, we're trying to draw the orbital notation of an atom with 15 electrons. We've drawn 10, so that means we have 5 left. So just keep that in mind, and let's keep going. So what's after 2p? It's 3s. Okay, so let's go on to 3s. Well, I hope I have enough room. 3s. And again, how many boxes is the s going to have? Well, according to our electron configuration here, s only has 1 orbital. So let's just do that. Let's draw 1 orbital. Oh, why is my boxes are getting so much worse? There we go. 1 orbital, and we're going to fill this orbital up with arrows. So we're going to do 1, 2. So we're now at 2, 4, 6, 8, 10. We're now at 12. So we almost have 15. We only have 3 electrons left. So let's keep going. What's next? After 3s, it is 3p. So let's go on to 3p. All right, 3p. And again, it's a p orbital. So how many orbitals? No, it's a p subshell. So how many orbitals can it hold? It can hold 3, right? It says it right here. P has 3. So we're going to draw 3 boxes here. 3 boxes. All right, 3 boxes. 1, 2, 3. They're not the most perfect boxes in the world, but they're mine. All right. Now, okay, so we only have 3 electrons left, right? Because we had one with 15. You know, that's what we were trying to draw, was an atom with 15 electrons. So now that we have, I think we already had 12, right? 2, 4, 6, 8, 10, 12. Yep. So we just need to draw 3 more electrons. So we're going to do 1. And again, I'm not going to draw a down arrow just yet, because we have to have all up arrows before we can have a down arrow in the same energy level. 2, 3. So we got 3 arrows here, and I believe in total this is 15, right? 2, 4, 6, 8, 10, 12, 13, 14, a 15. Okay? So this is the orbital notation. All right? Oh, one other thing. I should mention this now before I forget. If you guys want to, you can submit this as an image if you want to, because it's really hard to draw boxes using Word. So if you guys want to just, if you guys just want to draw your answers, take a picture of them and then submit them that way, that's totally fine. Okay, so just keep that in mind. This is the one exception I'll make. Normally I don't allow that, but I will obviously make an exception here. Okay, so that's example 1. Why don't we try a few more? We'll try these other 2 examples, and that should give you a good idea of how to do the assignment. Okay, let's try a kind of a hard one. Let's try one with 24 electrons. That's a lot. Okay, so let's try that here. Let's try one with 24 electrons. Get out of here. Okay, 24 electrons. Well, we're going to do what we've been doing. Okay, we're going to start with how they fill up, right? The first thing I do is fill up 1s, and I'm going to go a little bit quicker because, I mean, it's 24 electrons. But we'll start with 1s and we'll keep going, all right? And maybe just try and follow along with me instead. I'll try and explain my thought process, but let's try and be a little bit quicker. So we'll start with 1s, all right? I'm going to try and draw this a bit smaller. 1s. I know 1s only has one orbital because it says s has one. All right, so it's going to go up arrow, down arrow. Okay, so that's 2. Okay, so that's 2 electrons accounted for. Now we're going to go on to 2s. So 2s, same thing, only has one orbital. All right, so, and I'm going to fill up those electrons. So we have 4 so far. We only have 20 to go. Now we're going to go on to 2p. And I know 2p has 3, right? 2p has 3 orbitals, so I'm going to draw those. 1, 2, oops. 1, 2, 3. And again, look at how I'm filling these up. I'm always making sure that I have them filling up like the up arrows before I do the down arrows, because that's what Hund's rule says. It says they're only occupied by one electron spinning in the same direction before any orbital will receive a second electron. Now that all 3 of these have the same, electron spinning in the same direction, I can now fill in the rest. So 1, doop, doop. All right. So let's see, how many electrons do we have now? 2, 4, 6, 8, 10. Oh, okay, we only have 14 more to go. Let's keep going. Now we're going to go on to 3s. So 3s has one orbital, one box. So I'm going to draw that box. All right. It's going to go bop, bop. The s's are pretty easy. Okay, and so great. Now we have 2, 4, 6, 8, 10, 12. Sweet. Only have 12 more to go. Next is 3p, it looks like, right? The next is 3p. So let's do that. 3p. 1, 2, 3. We're going to go up arrow, up arrow, up arrow. Then we're going to go down arrow, down arrow, down arrow. Great. So how many do I have now? 2, 4, 6, 8, 10, 12, 14, 16, 18. Wow, only 6 more. All right, after 3p, we go on to 4s. All right, 4s. Seems weird, right? Seems like why aren't we going to 3D? Why 4 then back to 3? Don't question it, just accept it. All right, so 4s. Again, s only has one orbital. We're going to fill that up. 1, 2. Great. So now I believe are we at 20, right? I don't know why. I immediately forget these numbers right after I count everything. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 4 more. Okay, what's next here? After 4s, it's 3d. I think this is the first time we've seen d. Now, d look at d, right? It has 5, okay? It has 5 orbitals. So we're going to draw 5 boxes. 1, 2, 3, 4, 5. My boxes are not great. Yours will be better. Oops, 5. Sorry. Yeah, these aren't great boxes, but that's okay. This represents my 5 orbitals that are in my d subshell. Okay, and we only have 4 more arrows, so we're gonna go 1, 2. That's a terrible arrow. 3, 4. And I want to keep going, right? But I can't because I'm out of electrons. I am all out of electrons, okay? Right? Because we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23, 24. Okay? And that's how you do it. All right, so let's try this last one. It should be a lot easier because it's only 9. And that should give you a good understanding of how to complete your assignment. Or at least the first part. We'll go on to the second and third part later in just a bit. Okay? Okay, 9 electrons. Let's do one that has 9 electrons. Should be easy because, again, we're just doing the same order, right? We're going to start with 1s. Oops. Start with 1s. Okay, so let's fill that up. 1, 2. Then we're going to 2s. 1, 2. Then we're going to go on to 2p, which has 3 boxes, or 3 orbitals. And we're going to go 1, 2, 3, let's see, 2, 4, 5, 6, 7. Bam. All right, let's see how I did that, okay? Okay, now notice, I filled up these 3 first, right? Because they all have to be pointing upwards before I can get those down arrows going, right? So everything in the 2p section, because these 3 orbitals have the same exact energy level, right? Because these 3 orbitals are all 3 of them are 2p. So I want 1, 2, 3. Now, in total, right now, if you look at these electrons, I have 2, 4, 5, 6, 7. I only have 2 more electrons I can distribute, so I'm going to start filling my down electrons. And that's it. I can't do anymore, right? Because I'm out of electrons. Because this atom has 9 electrons, so I can't do anything else. All right, now that's how you do electron configurations. So for this assignment, it gives you an example here. For these 3 problems here, hopefully that'll help you. All right, let's go to part 2, quantum numbers. Now, quantum numbers, I'm going to just tell you, this one's actually not too hard because all you have to do to answer this, all you have to do is look at this chart and figure it out from there. I'll show you what I mean by that, though. Okay, I'll do number 4. I'll just do number 4 for you. It says, what are the first 2 quantum numbers for the electrons located in subshell 4D? Okay, for the electrons located in subshell 4D. All right, well, think about these quantum numbers, right? So remember, the first thing is the, oh, it doesn't show you here. There it is. First thing, the first number is the n, okay, the principal quantum number. Well, it's pretty easy, right? See how it shows you, here's the principal quantum number? Well, it tells you right here, it's subshell 4D. Well, that 4, that's the answer right there, right? The principal quantum number, that's the first quantum number. And since it already says that this electron is in 4D, guess what? Your answer is, and I'll just type it in here. Oops. Your answer is n equals 4. That n should be lowercase, but it's just going to keep capitalizing it. And then what's my next quantum number? I believe the next quantum number is your angular momentum quantum number, which is L. Okay, L. So let's do that. L equals, what does L equal? Okay, so it says that it's in D, right? Subshell D. Well, according to this, according to this for D, it says that your L equals 2, okay? The quantum number in a D is 2. For P, it's 1. For S, it's 0. So for D, it is 2. So we'll put that. L equals 2. Well, that's pretty easy, right? Let's keep going here. You know what? We'll just go through these together. How about? What are the first 3 quantum numbers for the electrons located in subshell 2s? Let's see here. The first 3 quantum numbers for 2s. All right, well, n is pretty easy, right? N equals, and let's capitalize it again. N equals 2. I mean, it just tells you right there. If it's in 2s, then n equals 2. The quantum number is 2. N equals 2. All right, what's our L? What's our angular momentum number here? Okay, so it said that it, let's see, what was it? It was S, right? I believe S is 0. Yep, look at there. L equals 0. So there's your answer. L equals 0. All right, so those are pretty easy. How many electrons can be held in a sublevel L equals 3? All you have to do is find this. See where it says L equals 3 right here? You can also, I think you can find it here as well. No, you can't. Oh, yeah, L equals 3. Look at that. And it says number of orbitals. So the number of orbitals is 7. Now this question's asking you how many electrons can be held in that. Well, if the number of orbitals is 7, and according to Hund's rule, or I'm sorry, according to this rule, it says only 2 electrons can fit in an orbital. Well, if we have 7 orbitals, and each orbital can hold 2, what's 7 times 2? 7 times 2 is a 14. Oop. So I guess I'll put my answer up here. It's a little awkward. But yeah, 14. It can hold 14 electrons. Okay, how many electrons can be held in the energy level n equals 4? All right, let's see here. Can we find that? Let's tell us anything. No, it won't. Okay. I've already forgotten the question. How many electrons can we hold in the energy level n equals 4? Okay, n equals 4. Oh, look at that. It just tells you right here. N equals 4. Total electrons and energy level is 32. Okay, it is 32. So there's our answer right there. Our answer is 32. Oops. Electrons. How many electrons in an atom can share the quantum numbers n equals 4 and L equals 3? Okay, well that one's actually, it sounds kind of scary, but let's think about this. We just answered that n equals 4 can hold up to 32 electrons. And L equals 3. Let's look at L equals 3. How many electrons can be held in L equals 3? Oh, well, I'm in the wrong spot. Sorry. Okay, so L equals 3. Oh, we already answered that, right? We know that in this sublevel, you can hold up to 14 electrons, right? So that's got to be the answer, because you can't hold more than 14. So you can have 14 electrons. Let's try that again. You can have 14 electrons. Okay, right? Because n equals 4, that just means it's like a very far out level, and that level can hold up to 32. But of those 32 electrons, 14 of them can be found in the L equals 3, okay, the F subshell. All right. For part 3, electrostatic forces, you guys should be able to figure this out. It's right here. What do you mean invalid session? Hold on, guys. Okay, sorry about that. But yeah, for this one, you should be able to figure it out. It's right. It talks about everything right here, and I think on this page. Here you go. Right. So here's your answers right here. Literally, like here's your answer. So I'm not going to go into that one. It also says, according to Coulomb's law, how would because it's asking you to draw the electrical field lines between two negatively charged particles. Well, look here. It says if something has the same charge, so you have two, well, these are two protons, but let's say you have two negatively charged particles, it's going to look the exact same, right? They're going to be repelling each other. So that's your answer right there. The only difference is it would have a negative symbol instead of a positive symbol. According to Coulomb's law, how would the electrical force between these particles change if they were moved farther apart? Guess what? Your answer is somewhere over here. Don't worry too much about the equation, but look here. It says here... Hold on. Here. Basically, as the distance between charged particles decreases, the force between them increases, and vice versa. There's your answer right there. So figure out how to apply that to your problem. Also, an increase of electrical charge increases the electrostatic forces between them. Okay, so I believe that's... Oh, look at that. Question number 10 has that exact question. How would the electrical force between these particles change if the product of their electrical charge increased? So for part 3, you guys should be able to figure that out. For part 2, we went through it together, and for part 1, I went through that entire tutorial with these things. That should really help you out. If it doesn't, and you still need help, just text me and I'll call you. But please watch this video first. What's a weird thing to say that at the end? And again, you can totally draw, if you want to submit this assignment as an image and just draw it, you totally can. All right, you totally can do that. That's fine.